In last video, we have seen Pauli matrices related with spin operators, and now in this class, we are going to study their properties. So we know three Pauli matrices: sigma x, sigma y, sigma z are given by 0, 0, 1, 0, 0 minus iota, and then you have 1, 0, 0 minus 1. Now all these matrices, since these are related with the spin operator, which are Hermitians, so this first property is these Pauli matrices are Hermitian. These are Hermitian. If you see carefully, their trace of any Pauli matrix is 0, and if you calculate the determinant of any sigma j matrix, determinant is also 0. If you take any property number 2, if you take any sigma matrix and multiply by with itself, it will give you the identity of matrix. For example, if I take multiply sigma with sigma, 0, 1, 1, 0, 0, 1, 1, 0. So this will give me 0, 0, 1, 1, then 0, 0, 0, 0, 0, and then it'll give you 1, 0. So this is the identity matrix. Similarly, if you multiply sigma x with sigma y, you'll get iota sigma z, iota sigma j. Okay, that means iota sigma j. And if you take and this is equal to minus sigma y sigma x. Okay, that means if you take the commutator of sigma xy or ij, that is sigma x sigma y plus sigma y sigma z is equal to 0. Commutator is 0, sigma I sigma j is 0. And then if this is also true, then you can find the commutator sigma x sigma y will give you what? It will give you 2 iota sigma z. Okay, similarly if you take sigma y sigma z, then you have 2 iota sigma x. So here that means if you have a I j is there, then you get 2 I if I is there, 2I, and then you get sigma k, and you can put here delta ij also, delta ij. So what will happen here? This property, how can I write? Or this commutator I'm telling, commutator. If commutator is there, so commutator you can write commutator. You can write like say sigma I sigma j 2I delta ij sigma k. 2I delta j 2I delta j 2I delta 2I delta j 2I delta ij. So say if I, then you get I square plus I square, that is 2I. You get 2I. If delta ij will be 1 if I equals to j, and it will be 0 if I not equals to j. Okay, and if they are not equal, then what will happen? Then this will become 0. For any two anti-commutator relation, you can write this like this way. Okay. So we have seen square iota sigma is anti-commutator, and now there is a one more property, say sigma x, sigma y, sigma z, that is equal to I. And one more important property is there. If you have I, iota I, alpha sigma j, that you can write I cos of alpha plus iota sigma j sine alpha. This is very important property we are going to use, and this is quite easy to prove also. So suppose you have I alpha sigma j, and now this how can you write? You can write here as a k equals to 0 to infinite. You can write uh, x power k, x power, so iota alpha sigma j power k, and then you have a factorial k. Okay, so x 0 1 plus uh, x, so this is the I have opened the exponential. Now if you carefully see, if iota alpha sigma j power is say even means either 0 to 4. So if it is even, what will happen? What will happen? If it is even, you can write this as a iota square power k alpha power 2k and sigma j square power k. So this become -1. So -1 power k alpha power 2k, and this is sigma j square is 1 or k. So this is completed. So you can write uh, for even power you can write like this. If it k is 0, then this will become 1. And now for odd powers, what you can write for odd powers, I can write iota sigma iota alpha sigma j. Say the power is odd, 2k plus 1. In that case, how can I write? I can write here iota square -1 power k. Similarly, alpha power 2k plus 1 and sigma j square 1. So k1, so this becomes sigma j. So this way I can write. So now I can break this summation in two ways, even power and odd power. So I can write k equals to 0 to infinite, 1 to k equals to 0, 1, 2, 3. And now I'm breaking some powers. So this becomes iota alpha sigma j. I'm writing here 2k and summation 2k. Okay. So this and similarly now for odd power I am writing iota alpha sigma j power 2k plus 1 and factorial 2k plus 1. And here already we have seen how can I write power 2k like this. So this is independent of sigma. So k equals to 0, infinite. And now sigma square is I. Okay, sigma square is I. So here sigma square become I. So if you want, you can write I here. So now what will happen? This will become -1 power k -1 power k alpha 2k, and I is outside. Okay, and you have here 2k 2k, and then this I can write k0, k infinite, sigma j is there. Okay, so iota sigma j is there, and inside will be k minus k alpha 2k plus 1 upon root 2k plus 1. Now just we can solve it in one step. Now this is nothing. If you put a 0, you get 1. If you put 1, then this become 2, and this becomes square, and this become minus. So this is the basically cos series. Okay, what is cos series? Cos x is 1 minus x plus 1 minus x square plus x4. So this is 2 4 plus minus alternate plus and minus x6 upon 6. So if you put a 0 here, you get 1. If you put 1 here, then you get minus x square 2. If you put 3 here, 3, then this becomes 6. If you put now 2 become 4, 4 it will be positive. If you put 3, then it will be 6, and this will be 6, and this will be 3 negative. So this is a cos series. So I can write this is equal to, so my e power iota alpha sigma j is equal to I cos of alpha, and this is iota sigma j, and this is series of sign. If you put 0, then this become 1, 0, then become alpha and alpha. So x, so sin x series, x minus x cube upon 3 plus x5 upon factorial 5. Alternate. If I put 2, 1, so this become 3, and this become 3, and this become minus. If I become 2, become 5, 5, and this become 2. If you put 2, so this become positive, so this become positive. So this is sine series. So I can write this is the sine of alpha. So hence proved. So this is very important properties. We can going to use this again. Okay. So I'll stop here. Thank you.